Hello, good morning everyone. Today class is electrodynamics. In previous class we are discussed the potential function. Today we have to discuss wave equation and their solution. What is non-homogeneous wave equation for a scalar potential? We already learned in previous class. That is del square V minus mu epsilon dou square V by dou t square is equal to minus rho epsilon. We can do this by first finding the solution for an elemental point charge at time t, rho of t del V dash, located at the origin of the coordinate system, and then by summing the effect of all the charge element in a given region. In spherical polar coordinate system, del square V is equal to 1 by r square dou by dou r square dou V by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou V by dou theta plus 1 by r square sin square theta dou square V by dou phi square. Because of spherical symmetry, potential V depend only on r and t. Except at the origin, we satisfy the following homogeneous equation. Therefore, equation is del square V minus mu epsilon dou square V by dou t square is equal to 0. Substitute del square V in this equation. The equation becomes 1 by r square dou by dou r of r square dou V by dou r minus mu epsilon dou square V by dou t square is equal to 0. Let's take V of RT is equal to 1 by R U of RT. Differentiate V with respect to R. Here we have to apply the product rule. Dou V by dou R is equal to first function into derivative of second, 1 by R into dou U by dou R plus second function into derivative of first, U of RT into minus 1 by R square. Therefore, dou V by dou R is equal to 1 by R dou U by dou R minus U of RT into 1 by R square. Then differentiate dou V by dou R with respect to R. Therefore, dou square V by dou R square is equal to 1 by R into derivative of second function dou square U by dou R square plus second function dou U by dou R into derivative of first minus 1 by R square minus first function 1 by R square into derivative of second function 1 by R square into derivative of first function dou U by dou R minus the first function U of RT into derivative of second function minus 2 by R cube. Therefore, equation becomes dou square V by dou R square is equal to 1 by R dou square U by dou R square minus dou U by dou R 1 by R square minus 1 by R square dou U by dou R plus 2 by R cube U of RT. Here we have applied product rule in these two terms, 1 by R dou U by dou R and U of RT 1 by R square. So the equation become like this. It can be rewrite like dou square V by dou R square is equal to 1 by R dou square U by dou R square minus 2 by R square dou U by dou R plus 2 by R cube U of RT. Then we differentiate V with respect to t. The equation becomes dou V by dou t is equal to 1 by R dou U by dou t. Then differentiate dou V by dou t with respect to t. Dou square V by dou t square is equal to 1 by R dou square U by dou t square. Take the equation number 2, that is 1 by R square dou by dou R square dou V dou by dou R of R square dou V by dou R minus mu epsilon dou square V by dou t square is equal to 0. Expanding this equation, we get, here we have to expand only the term dou by dou R square dou V by dou R. Here we have to apply the product rule, the equation becomes dou by dou r square dou v by dou r is equal to first function r square into derivative of second function dou square v by dou r square plus second function dou v by dou r into derivative of first function 2r. So the equation becomes 1 by r square into r square dou square v by dou r square plus 2r into dou v by dou r minus mu epsilon dou square v by dou t square is equal to 0. It implies dou square v by dou r square plus 2 by r dou v by dou r minus mu epsilon dou square v by dou t square is equal to 0. We already find dou square v by dou r square, dou v by dou r and dou square v by dou t square. Substitute all this in this equation. The equation becomes 1 by r dou square u by dou r square minus 2r square dou u by dou r plus 2u by r cube plus 2 by r square dou u by dou r minus 2u by r cube minus mu epsilon by r dou square u by dou t square is equal to 0. We have to cancel 2 by r square dou u by dou r and 2u by r cube. The equation becomes 1 by r dou square u by dou r square minus mu epsilon by r dou square u by dou t square is equal to 0. It implies dou square u by dou r square minus mu epsilon dou square u by dou t square is equal to 0. This is the one-dimensional homogeneous wave equation. The solution of this equation is any twice differentiable function of t minus r root mu epsilon or t plus r root mu epsilon. But the function of t plus r root mu epsilon have not physical useful solution. It's not a physical useful solution. So we take u of rt. The solution u of rt is equal to function of t minus r root mu epsilon. Here the wave is moving along positive r direction with velocity 1 by root mu epsilon. The function at r plus delta r at a later time t plus delta t is u of r plus delta r t plus delta t is equal to function of t plus delta t minus r plus delta r root mu epsilon. This function retains its form if delta t is equal to delta r into root of mu epsilon or delta r by u, where u is equal to 1 by root mu epsilon. This is the velocity of propagation. It is called a velocity of propagation. From the equation of u of rt, we have to write v of rt is equal to 1 by r f function of t minus r root mu epsilon. That is, we in the first section we write v of rt is equal to 1 by r u of rt, and the solution is u of rt is equal to function of t minus r root mu epsilon. That is, the solution is substitute in the equation of v of rt. So v of rt is equal to 1 by r function of t minus r root mu epsilon. It is also can be write like this: v of rt is equal to 1 by r function of t minus r by u. For a static point charge, rho of t delta v dash at the origin is delta v of r is equal to rho of t delta v dash 4 pi epsilon r. Comparing this equation and the equation of v of rt, we get delta f t minus r by u is equal to rho of t minus r by u divided by 4 pi epsilon delta v dash. The potential due to the charge distribution over a volume V is V of RT is equal to 1 by 4 pi epsilon integral rho of T minus R by U divided by R into dV dash. It is called the retired scalar potential. Similarly, retired vector potential is A of RT is equal to mu by 4 pi integral V dash J of T minus R by U divided by R into dV dash. Okay, let us wind up the class. Thank you.